Education is not learning of facts, but the training of the mind to think. I have a small correction in it. We are not talking about facts in science. In science, we are talking about fundamentals. So Einstein is fully correct, but a corollary to it, when I go to my presentation on how to do a good research, I'll stress on the point that your fundamentals must be very clear. You don't have to memorize them, but you'll have to feel it, realize it, try to understand the physical meaning of it. Then you can apply. And if you are good at that, you can do any good research. So today, just an extension of this quotation, as I mentioned earlier, I'll try to talk to you the way I can inspire you to do a good research. All these topics, many of you might have listened to me many times. And I cannot reproduce it in a different way. Contents are same. Contents I cannot change, I can add. But I try to present it in such a way you can think about it. While you're listening to me, try to understand it and think what else you can do on it. Because research is never stopping somewhere. It continues. As I mentioned, that I studied shearing and ploughing. From there, through my continuous thinking, I went into extrusion. That was a PhD project. Then I came to varnishing. It's a new project, and CIRP has accepted 2 more machining region. One is extrusion region, another is varnishing region. And hopefully, in another 1 or 2 years, I'll come up with atomic machining, which includes everything. So fundamentals are there. They need extension, more clarification, addition, and so on. So what I will be telling, what I have done, and from there please think what you can do further on it. Never think that is the end of it. If you are a conventional thinker, you will think, oh, it has been done, what else I can do? If you think that, then you can never proceed. I'll give a few examples before I go to that actual content of my talk. When I started my EDM and ECM compounding together, simultaneous, I'm not an EDM expert, but I learned EDM through my research because I proposed compound machining, and in compound machining, you may not be master of that, but you need to be jack of the trade. So I had to learn something superficially, then through these questions and answers, problems and solutions, I'm still learning, I'm not yet expert, but I try to cover all possible areas on machining. So I think that could be one of the reasons why you are here in large number, because if you want to know about conventional machining, I hope I can teach with full energy, vigor, confidence, though I may not be 100% correct. Then I can talk about EDM, which I have learned through my practice, through the necessity. ECM, of course, I had to learn. And I had to learn grinding, milling, all these details, all the topics. I had to learn, practice, and do research, because that is very much necessary. Those who try to do research in machining, they say, yes, I'm a machining expert, I do not know about EDM. Those who do EDM, they say, oh, no, I know only non-conventional machining, I do not know about conventional machining. Those who do research on laser, they say, no, I'm a research expert on laser, I do not know anything else. And elite grinding, today, during this course, I'll try to talk to you about elite grinding, which absolutely an area. One of my colleagues I sent to Japan, because when I was a student, I knew elite grinding is going on in Japan. I knew about it. So I sent my colleague to have a few days training there, came back, we developed our machine, and we did elite grinding, which is a very wonderful area. And when I was thinking that EDM and ECM, can we compound them? EDM expert says, no, impossible, it cannot be done. But with my conviction, we have successfully done it, published a CRP paper, and it's very well-known area now. When I thought, I was compelled to think about compounding EDM, which is sparking, with arcing, which is welding. Then EDM expert, I have a colleague, I had a colleague who migrated to New Zealand. He was a real EDM expert. So I told him, let me compound them together, then I can do very fast EDM drilling, EDM hole, very quickly. He said, Rahman, whole life you were crazy, still crazy, give up the idea. Two diametrically opposite processes, you are trying to compound them together, impossible. I told him, EDM and ECM, two diametrically opposite processes. We have successfully done it, and with your help. So he was very encouraged. So we tried to do it, and with so many challenges and so on, I'm very happy to tell you that the student who did it very successfully, he's here today. So no longer he's my student, he's colleague, because he's teaching in one of the IITs. I will not tell you who is he. Maybe when I introduce that arcing and sparking together, I may request him to give the talk, because it is better to listen from the horse's mouth rather than imitating the horse. So if he agrees, I'll request him to give the talk, or even if I'm stuck, he can answer the questions. Rather than giving it a bad answer, we try to get a good answer. Okay, so having said all these, let me come to the point. I did all these things not because of fun, not because I wanted to learn a lot of processes, but I thought it is a necessity to do all machining processes, conventional, non-conventional, compound, simultaneous, to successfully do machining. And that's why when I was talking about this machining, different machining processes together, one of the listeners said, sir, some of the processes are not simultaneous. So how do you term them? I said, okay, hybrid. Then he said, why don't you say it's a compound machining, sequentially or simultaneously all covered in one term, compound machining. So I liked that idea, so I coined that term. When you do many processes together in one setup, I call it compound machining. And compound machining is very much necessary in micro-nano machining. All these things I'll justify later. So I was forced, or I felt the necessity to learn all the processes together, and the reason I'll tell you. After my PhD was on vibration, chatter vibration, and after doing that, while I was working on chatter vibration, I had to understand machining. Otherwise, chatter is taking place in machining. And if I do not understand machining, then how can I analyze chatter vibration? So I started learning machining while we are doing chatter vibration. And after learning chatter vibration, machining everything, where do I apply it? You should apply it. If I say, okay, now I know chatter theory, when chatter generates, how to control it, how to do this, that. So I thought that I'll apply chatter vibration to determine the criteria of the performance of machine tools. If this machine chatters earlier, and that machine chatters later at a bigger depth of cut, then definitely that machine is better. So it is one of the performance criteria for machine tools performance analysis, so that the users or customers, they know how to distinguish the performance of two machines, how to determine the limitation of performance of a machine. And that is very much used now. Now you'll see a lot of people are selling the software determination of performance analysis of machine tools using chatter vibration. And I'm very happy to say that I initiated that work, and I found, then I thought, chatter I did, it is being applied. Am I at the dead end of my research? I said, no. And then I started thinking about something different. And to get something different, if you don't get something different, our funding authority is very rigid, very strict, they don't give you funding. The funding is huge in Singapore, but to get funding, you'll have to justify that you are doing something new. Believe it or not, after 10 years of research in NUS, I took a break of 2 months, went to Japan, and visited in 60 days, I visited about 29 big labs. Name it, I was there. Whoever is doing machining, I was there. Hitachi lab, they have 3,000 engineers doing machining. Can you imagine? And I was there, and when I was visiting, in one corner I saw they're covering the corner. I asked them, what is there? He said, oh, no, it's from Singapore. You'll not understand this. So, when restricted food becomes very favorite, so I thought, no, I will have to learn about it. So I said, why don't you show me? No, these machines are all covered, the dust is there, we don't like to open them. I said, please. But luckily, the director of the lab was an ex-graduate of TIT, where I graduated. So I said, do you want me to request the director to show me the machine? And he said, how do you know? I said, there is. Oh, okay. So they opened it and saw that they were doing micro machining. And all these background stories I tell you, then I got the idea, and they were doing micro as well as nano. Finally, very good news is that after a few months they came to NUS and said, would you like to do research? We will fund it, and all these things. Anyway, so for my own research, I had to get a new area, and the story I have told you many times, and why I went into micro machining area. This is a new area. Moreover, the necessity from my own life, I think I have told you many times. I had ulcer. How many of you have listened that story that I had serious ulcer? So 2 of you. Would you like to listen to me this story again? Okay, quickly. And my professor, you are recording all those. I hope it should be all right. Okay, relevance. I'll talk to you. I think I'm covering something without going into the slides. Okay, so what happened? I'll go a little away from this. First, the most important thing in your life, please try to remember, you should try to remain relevant in life. How many you have listened to my relevance talk? None. Okay. Relevance. Once I gave a talk in IIT. First of all, I gave a talk in BARC, long time back. And I started saying why I went into micro machining, and I started from relevance. And then in IIT Bombay, I gave a talk on micro machining without talking about relevance. So Dr. Balasubramaniam stood up and said, Prof, today's talk is incomplete. I said, why? You have spoken about micro machining, but you did not talk about relevance. Because without that relevance, micro machining doesn't gel very well. So I had to repeat quickly about relevance in life. Shall I repeat that today? Everybody, please try to remain relevant in life. If you try to remain relevant in life, research, everything is very smooth. Very quickly, first of all, I'm sure all of you have learned through experience, you should be very relevant to your family. If the wife says, my husband is stupid, useless, then very unhappy family. If son says, my father, oh God, worthless, family life is very unhappy life. If brother says, my second brother is really dumb, stupid. So everybody should try to find that as a husband, am I relevant to my wife? Does he appreciate that? Oh, my husband is great. Not in front of me, but at least behind me. And wife says, oh, my wonderful wife, she helps me a lot. So this way, that family is very happy family. But how to do it, I do not have my technique. I cannot express my technique to do it, but please try to learn about it. Correct? If you try to find fault, you can find fault with anybody and everybody. But if you try to find a solution, then you can always get a solution to make your own life happy. An intelligent man, I'll add one more quotation, an intelligent man is an intelligent man who knows all important things. And what is the difference between an intelligent man and wise man? Have you ever thought? Have you ever thought? I'm going too much away, but today I told you that I will not stick to my text. I will definitely cover my text, don't worry. Even if I take longer time with a poor health, but I'll do it. But I think let us have, I've traveled a journey. I'm now 70 by the grace of God with your prayers. So I should share my experience with you, which may help more than, because my text is there. Moreover, before I forget, I have published a book under Elsevier on advanced machining processes. There are 19 chapters. Most of the chapters are written by me, about almost all the chapters, except few. So all the lectures are there in that book. Here I'll show the slides and refer that book. You can get the PDF, you can take out PDF printing without any charges. It is free. Advanced machining processes. It is under, I'll give you more details. It is published by Elsevier. Okay, so all these are there, more details. Coming to that, where I was. I was there about family. Oh, intelligent man wise. Okay, okay. There are 11 criteria. I need to open my email to tell you. If we summarize everything, an intelligent man can become a wise man. And intelligent man can remain intelligent. But without not being intelligent, you cannot be very wise actually. Intelligent man knows all intelligent things. But an intelligent man likes to argue because he's intelligent. You'll have to listen to me because I'm intelligent. But intelligent man becomes wise to know where to draw the line. If I know, if I cannot convince him, I'm not wise. I know, but I'll have to feed him the way he likes it. That means I'll have to be acceptable, I'll have to be reasonable, I'll have to be compromising, I'll have to have giving attitude. Please remember that. So, husband may be very intelligent. If he thinks, oh God, my wife is a stupid lady, why did I marry her? He's an intelligent, but he's not wise. So let me skip that chapter about family. Now, most important thing in our professional life, social life also you need to be intelligent, otherwise in the society, in the community, if your colleague says, oh my colleague, he's a good guy in research, but he's a stupid guy, then you are not wise. So you'll have to have an atmosphere in your community of research. My students will be the witness how I compromise the whole group of, we are 7 researchers, all I inspired them. We are 14, 7 went on software side, 7 remained in machining side. And everybody was doing island research, but I inspired them, brought them together, we did machining only. EDM, machining, one was teaching only machining, very fantastic guy, one was doing 3D printing. Then all these manufacturing guys, I tried to gel them into machining. Though some of them were doing 3D printing, they were convinced that if they take the help of machining group, so manufacturing group in general, so professionally, wherever you are, now in most important thing, if you do not do relevant thing in profession, for instance, as a researcher, if you write a research proposal, which is not required, it's not in the government list of funding, you may be very proud, intelligent, oh God, I did it, I must get the money. You will not get it. Because you will have to know what is the funding authority is looking for. And funding authority is not looking for giving money to their projects of their own dream. It is a project which the country needs, because we are all mechanical manufacturing engineers. So you will have to think, whatever they think, you will have to think what the country needs in manufacturing. Okay? So that way, and I thought that what is next in machining? Without machining, we cannot do anything. I put a challenge that if you do not know machining, you cannot do manufacturing. Manufacturing, whole industry will collapse if there is no good machining industry. Because everything you try to make, you will have to take the help. You can say plastic molding and so on and so forth. After all, you will have to make the mold to make the thing short. So machining is the fundamental of manufacturing, and manufacturing is the fundamental of the growth of an industry, of the country. Look at China, booming manufacturing industry. Look at America. I should say the other way, correct? So manufacturing is most important, and machining is the basic element of manufacturing, the basic element of development of a country. I think I'm deviating too much. So you'll have to think where you should put your research, and everything is moving into that direction of more and more precision. Coming to the point of precision, let me try to consolidate. So you'll have to think what type of project, what type of research you should do, and you should try to remain relevant. If you think of relevant to the institute, to the community, to manufacturing, then there is no other option than moving machining into higher and higher level. Now, coming to machining or manufacturing, what is the most important thing you think in machining? Why we are moving from milli to micro to nano and atomic level? What was the reason? What is the main reason? Let it be very interactive. Please participate. New products coming out. Huh? Size effect. Tolerance. Quality. Okay. What is the difference between a macro product and a micro product? If your product is okay, I cannot have error more than 2% or 1%. If it is a milli product, 1% is also a milli. But when a product is micro, 1% of micro, machines were not in micro accuracy. So we are moving into micro accuracy, nano accuracy, and so on. And when you go into smaller and smaller product, finer and finer product, our accuracy becomes most important thing. Accuracy means correct dimension. We should dream of making product which has no tolerance. Do you think tolerance is a must? Is tolerance a must or not? Tolerance is a must. Okay, I think you are dragging me too much into debates. Okay, please. I say no. Tolerance will be the talk of the past. Can we get out of tolerance? No. Anybody who dares to challenge, yes, we do not need tolerance. No? Depends on? Tolerance should be the talk of the past. But how to do it? I tell you one thing. Tolerance, why do we need tolerance? Because we cannot get exact dimension, correct? Why we cannot get exact dimension? Okay. Most important thing is that tool wears off, correct? I set a dimension, the tool wears off, I want to machine a shaft and diameter is 50 millimeter, no plus minus, zero tolerance. If whatever tool I take, it will wear off. So dimension will be different. We need tolerance. But have you thought, what is the basic condition of tool? Tool must be harder than the workpiece. Correct? If my tool is infinitely hard compared to the workpiece, do we need tolerance? No? Correct? There will be no tool wear. Can we think of a combination of a tool and a workpiece where the tool does not wear off? Can you think of a tool which will not wear off if we machine that particular material? I give you the choice. If I cut leaves with a knife will never wear off, correct? So similarly, because steel knife is infinitely sharp compared to a leaf. But is there any material which is very widely used and its use is increasing tremendously, and a tool which is hardly used, after the tool exists? I've given you enough hint. We are not interactive. Is there any tool which is infinitely hard compared to workpiece? Aluminium and diamond. Do we need tolerance? In 1985, when Nissan started machining their aluminum wheel hub using diamond tool, everybody ridiculed them. To kill a mosquito, they are using a machine gun. But now everybody is doing it because you do not need any tolerance. So, tool and workpiece combination. That is again process bound because you are talking about turning or milling. Correct? But even with diamond, can you machine tungsten? There will be definitely tool wear. Correct? So we are again facing the barrier that tungsten and diamond. But we need to machine tungsten because all the molds, plastic molds for machining plastic, making plastic components, we use steel mold. But when you try to machine or mold the glass, steel mold is useless. Life is very short. Error will be there. And lens, you cannot allow any tolerance. You'll have to have 100% glass mold, because high performance molds must be glass. And the trend has come, and the mold must be of tungsten. How will you machine it? They machine it and they grind it. Is it the right process? Right or wrong? Machining and grinding and then polishing, is it the right process? I think I'm asking too many questions. Are you bored with me? No, grinding is never a high precision machining process. Whatever you call it, after grinding you do polish, you get a mirror finish. You can challenge me. Yes, I got mirror finish. But can you guarantee the form error? Zero form error. Impossible. I challenge. If you cannot have form error, zero form error, then how can you machine a high precision lens where you will have no distortion? So you will have to have a glass mold, tungsten mold, to have glass lens. And if you want to have a glass lens, that will give you high efficiency, perfect reflection. Plastic molds not. So the necessity is compelling us to move into better and better product, higher and higher quality, harder and harder, but we are getting restricted because we do turning. If we do grinding, error is there. We cannot tolerate error. So what to do? If you know that, yes, I know machining, that's not good enough. You'll have to know other processes where you can conveniently machine tungsten with very high accuracy. Because you are convinced that polishing will destroy the form accuracy, so you'll have to have other machining processes, which is, I'll be introducing, elite grinding, which tool and workpiece do not come into direct contact. Even if there is contact, accuracy is continuously taken care of. And you can think of other processes. ECM is extremely perfect, but ECM alone is very slow. You'll have to go to EDM because material is conductive. So you can do EDM, ECM, compound. So you'll have to know, because our enemy is error. We cannot have tolerance. We'll have to get rid of tolerance. So you'll have to know which machining process is to be applied. If you become very confident of metal machining, we do not do EDM, ECM and all these things, you cannot claim to be perfect man to do manufacturing. So you'll have to learn all the processes. Superficially maybe, because experts are there to impart his knowledge to you, to share knowledge with you. But you'll have to know what can be done through which process. Okay? My intention of this long journey is to tell you that you'll have to know compound machining, so that when to apply what. And for that, why compound machining? Because most important enemy of error is setup error. If you do turning here in this machine, EDM in another machine, your component is in micron. Setup error is more than few micron. So what are you doing? I will not name the person. There was a student from one of the NITs. He came and asked me that he is doing ECM. The error of machine setup is 5 to 10 micron, and he is doing micro ECM. And he is trying to make an electrode which is micro accuracy. I said, what? Machine is not accurate in micron. You are trying to do research on micron, making an electrode of micron accuracy. Your setup is wrong, your machine is wrong. So these are the points outside discussion. So you'll have to be very particular about the device you are using, the process you need to use, and if multiple processes are needed for the same product, which is usually you cannot just, one process may not give you the right product. So you'll have to know, so you'll have to think about machining as a compound process. So my first talk will be on tool-based compound micro nano fabrication. To bring you to this, I had to give such a long talk. All right? So I'll be talking about this topic today. And next topics will be because I'll start from turning. So turning, everybody knows about turning, so I'll be talking about more on advanced turning, which is diamond turning. I'll be introducing the terms extrusion, where you can get nano finish. From extrusion, I'll be talking about varnishing, which is recently published in last CIRP. Then micromilling. Micromilling, I'll be trying to concentrating on micromilling, you know, many of you, but how to do machine brittle material in ductile mode in milling. Again, when I took this challenge of machining brittle material, and I'll tell you the story, a student was very upset. How can you do ductile mode machining of brittle material? And he had to do it. He's a very brilliant guy. Then micro EDM, and again simultaneous EDM and ECM, which was a challenge. I'll talk about elite grinding, and then as I told, I'll be talking about art of doing good research, which is very necessary. All of you are doing research, but I want to share my experience, how to do a good research, how to write a good paper. If good research, then good paper and good publication. And I'll again share my own experience. I'm a visiting professor in one of the IITs, and some students say, sir, how come we cannot publish paper? So I told them those experiences I'll share with you. And then we'll have discussion. So this is all. Let me start my today's talk. Yeah, here is the quotation from Albert Einstein. I told you already. I should have put it first. So now, one of the paper I presented somewhere in 4M in Germany. That was a keynote paper. So that time, all the students were working, students plus myself, Asad my student, Tanvir is my student, Masaki was an expert from Japan, Y.S. Wong is my colleague, and H.S. Lim was my colleague as well as business partner. So usually, I do a research in a team, and I encourage all of you to share your knowledge with a team. Then you get, I see many of your, many researchers, they are alone. Please don't do that. Try to form your own group, share, and it's like a lamp. If you share, number of lamps increase, but your knowledge does not decrease. But you get a wider horizon of research, wider scope, publication goes up, and try to stick to not many areas, but don't run for the area where money is. Put in many intentional effort to do few areas only, not much. Okay, so compound I have already discussed. I'll stick to micro, and then I'll go to nanofabrication. Relevance I have already spoken. Relevance comes from necessity. Now necessity part, my life, did I tell, I told you that I'll tell my whole life story. Did I tell that? No, I didn't, okay. Quickly I'll tell that. After my PhD, I wanted to go back to Bangladesh I wanted to be a politician, so I wanted to go back to Bangladesh to do politics, but my supervisor, my father wanted me to be a teacher, but I promised I'll do my PhD, but not teacher. So, but a teacher in Japan, he convinced me that I should be a teacher. So father and my teacher, that created the pressure on me. And very quickly I'll tell my father's trick. My father says, I was working in a Japanese company, and my father says, he teach for a day to show that in the village people will believe that my son did his PhD, otherwise they will not believe me. Anyway, so that was the trick. And my teacher wanted me to be a teacher, so I ended up doing teacher. Now, when I was working in a Japanese company, my professor wanted me to have experience, industrial experience in a machine tool company. I was working there, and my professor, again, very quickly, he says, I never give a PhD degree anything less than 5 years, usually within 5 to 8 years. So I told him I want my PhD degree in 3 years. He said, well, impossible, but you can try. So I tried hard, and it was really hard work. One day when I was sleeping in the couch in the lab, morning he came and saw me, and he says, hey, I asked you to work 12 hours, not 24 hours. I said, no, sir, I'm trying to strike a balance. And anyway, within 3 years he gave me degree. He gave me degree, I think I earned it. Just to add, anyway, I will not say how many papers I published during my PhD. Then he wanted me to have industrial experience. So during my PhD, I already developed ulcer. It's hard work. Then I went to work in this company. My ulcer became serious. So my boss wanted me to go to a hospital. They said they will inspect me. I said, fine. But believe it or not, they tied my hands and leg against a table. 2 guys were holding my hand and 2 guys holding my leg so that I cannot move. And they introduced a lock so that I cannot bite. And he slowly introduced an endoscopic camera tube, which was 10 millimeter in diameter. It was very painful. And he was explaining the interni doctors, they all enjoyed, but I suffered. So after that I decided I'll never go for inspection. So after 2 months, I was all right, but I didn't go for inspection. So the doctor was insisting, and I pretended I have fever, cold, all this. I cannot go. but he complained to my supervised boss, and boss says, "Hey guy, why don't you go?" I said, "It's very painful." So my boss told the doctor, "It is painful, he doesn't want to go for it." The doctor says, "Oh, no, no, no. That time camera was 10 millimeter in diameter tube, now it is only 2 millimeter. And I went. Nobody was pressing me or no, nothing. And she introduced. And I didn't enjoy it, but it was okay. Then I saw everything is fine, everything done. So that day I said, hey, micro can do really miracle. So I decided to micro, and my micro journey I told you when I went to Japan and visited the lab, all this. So finally, I am very happy that I picked up an area which is very relevant, and you also, I'm sure, have picked up an area which is very relevant. From now on, you take it forward. Okay, so all this justification, I will not tell about that whole lecture. Everything is moving into micro and micro. Now, these things I have already told you, that you can read the slides later. All these processes are there to do micro machining. But I thought, no, if we do all these things, non-conventional machining, then the problems are there. You cannot have three-dimensional structures. You can only have low aspect ratio, and again, limitation of what is there, conductive, non-conductive, this and that. But whereas, if you go for machining, turning, milling, EDM, wire EDM, and advantages are plenty. Any machine, any material you can machine. Material removal rate is very high. 3D features you can machine, and you can have millistructure with micro features, and you can have very high aspect ratio, machining hard materials, and most important thing is very low investment. So judging all these things, I went for micro machining. Now the problem when I tried to do micro machining, there was no machine actually, because all this, please carefully listen to me. Machine tool, if you think micro machining you can do in any machine you can do it, but you may not get micro accuracy. Our struggle is to get the accuracy so that we can get repeatability. So machine must be highly accurate, and positioning error, everything should be almost zero. And most other thing is that you will have to know the process. If you think a conventional process and microprocess are same, it's not true, because you will have to know the compound process. That's what I told you already. You will have to develop hybrid process, and micro machining, when you do it, it must have the measurement system on the machine. Those who say, no, I don't need measurement system, then you are wrong, because if you cannot measure the dimension on the machine, that machine is useless. I should not say useless, but once you unclamp it, take it for measurement, bring it back to correct the dimension, shaft itself is 10 micron. So how you can assure the clamping accuracy? If not, then it's done. Okay, so that's why you will have to, you have seen that, you will have to do compound machining. You develop, if you buy an electrode from the market, let us say 50 micron hole, you buy an electrode of 50 micron, you'll have to rotate the electrode, clamping error is there, ultimately you will get a hole of 100 micron, 150 micron, whatnot. Whereas if you machine the electrode on the machine, and on the same machine if you do EDM, you will get only erosion error. And if you can measure it correctly, you will get same erosion error every time. You will get the repeatability of the hole. Even if it is 50 micron hole, it will be perfect every time. So even to machine tungsten, if you can measure the parameters correctly, control them, you will have zero error every time. So tolerance, I'm sure you will believe that it will be history of the past. But it's not easy. It can be achieved, and it should be achieved, because that is what we need. And if you can do that, and you're successful. This is the process, turning process, you do it, and after that, after getting the shaft, you do EDM. Okay, let me, machine tool, there was no machine tool, I've already told. This slide also I'll skip. So first thing for me was to develop a machine, multi-process machine to do compound machining, combining conventional non-collision everything, and so that's why we had to develop it. Now, so we had to develop a miniature machine. These are things, I think we will skip all these things. Why miniature machine tool? I'm sure all of you know about it. If you try to make a huge machine and try to make it compound for a small, again, killing a mosquito with a machine gun, you don't need it. And most importantly, all things you can do it on a small machine, your cost is so low. These things I'll skip. Finally, we got a machine which can do multi-process machining. Okay. And having said that, when we started the machine, we did it only micro, turning, milling, EDM, ECM, wire EDM, everything. Then we had to move on. I hope you know why we added laser. Because there was a request from Australia. Somebody once on a plate of 10 inch by 10 inch, they measure in inches, 10,000 holes, exact 50 micron in diameter, 10,000 holes on that plate, and as fast as possible. And it must be very accurate as well. So what was the solution? If we do by EDM, it will take days. So we thought immediately that we'll do laser and finish it with EDM. So we had to add laser, and we are selling micro machine. People are asking, no, your machine is quite slow, we want to do industrial job. We have changed our EDM power supply, which we have not started marketing yet. It will be there. So we keep on adding, and now we are thinking to add arcing and sparking, welding and EDM together. So another dimension will be added. So this way we are adding on more and more dimensions. Controller is our own controller, where you can compound conventional and non-conventional machining. Sorry, it's not talking about, don't consider it as a commercial talk, but I'm very happy to share with you. It's a wonderful, extremely highly accurate. This is a hole which is 50 micron in diameter, EDM hole. And a conventional hole is on the top left side. If it is 50 micron, you cannot see that it is so much, it has so much of error. On our machine, it is like that, as if it is a zig boring hole. As Professor Joe Smith mentioned, just buy a conventional micro milling machine from Kern, which is $350,000. With all these functions, our price is much, much cheaper. Anyway, and if it is a wire cut piece, it is so accurate. And coming here, as I told earlier, that I gave the student to a student from IIT Delhi to make a shaft which is 50 micron, and we went through challenges and so on. Finally, he did it in 2 weeks. I hope you know the process, correct? How to do a 50 micron shaft. Am I moving too fast? It's okay. Okay, how many of you know that how to machine a 50 micron shaft using turning? No? No one? I'm sure some of you know it. How many of you know about it? Many of you. Those who do not know, for them, those who know, please keep quiet for a while. Why you can't do 50 micron shaft? Deflection. So deflection is the main enemy, because there is a cutting force which will cause deflection. When you do research, when you have a problem, try to analyze why I cannot do it, and try to get a solution, physics solution, mathematical solution, whether it can be done or not. The first, if you know the cause why you cannot do it, it is deflection, and deflection is caused by force. Correct? So then the IIT Delhi student, when he said surrendered, I told him, I write the equation for you, then you can do it. And then he says, no sir, there is no equation to. I said, no, don't try to forget the past. There is an equation which combines force and deflection. Anyway, I wrote it for him, and he jumped and said, oh, there was such an equation. Okay? What happened to the equation? It is hidden. Shall I take a small break? It is there. You know the equation, delta deflection is equal to FL cubed by 3EI, correct? FL cubed by 3EI. E and I are constant depending on the material and the configuration. You take force and length. So you can control the force if you can control the force as minimum as possible, and then a deflection. So when we talk about turning, what we try to do, everybody thinks longitudinal turning from right to left. So if it is length is, let us say, 10 millimeter, you try to machine from a 6 millimeter diameter bar, you go up to 50 micron. On the way, it will bend so much that you cannot carry out machining. So everybody will think, oh, turning means this. No, why don't you think that way, that your deflection will tell you for a cutting force of so much, what will be the deflection. So if you remain within the elastic limit of deflection, and that way you can calculate your length of overhang of the workpiece could be 0.5 millimeter for a force of 1 Newton. So all these we calculated and experimentally verified and found for what force, what will be deflection for what length of overhang. So we went into step turning. There is a pointer. Okay, so you calculate the step. You calculate the step, what with the length of overhang. Your tool is here, so this amount of, from here to here, second dotted line, you continuously go on machining up to the diameter. Then, when you go to 50 micron, it will still be within elastic limit of deflection. Is it clear? And then you go to the next step. Now, you may ask the question, if you do the step machining, there will be error, which is not true, because if your machine is correct, machine is rigid enough, and you control the cutting force, you'll definitely get a straight shaft. Experimentally we found it, and if you look at these 50 micron shafts, all are straight. Of course, some people touch it and they bend it. So you shouldn't, after machining, you shouldn't touch it. So 50 micron shaft is not a problem. And the student did it in 2 weeks. This is my dream project. He took the challenge. He did it successfully. I paid him return airfare. He was very happy. Okay. Now, this pin is 3 millimeter in length. So many features done so accurately. This paper was published in AIMTDR. Sorry, MTIRA, Machine Tool Research Journal. So the student who did this work, he finished his PhD last year on burnishing. Okay, now, when you develop this machine and we can do 50 micron hole, Dr. Mori, the president of Mori Seiki, came and saw this. He said, wonderful machine. He went to Japan to tell Panasonic to buy our machine. So Panasonic was very happy, because once they were developing EDM machine, they stopped it, so that they thought they will use our machine. So they came, and so they saw 50 micron shaft hole. We machined a hole with 52 micron diameter. They were very happy, but they were not willing to buy the machine. They say, well, we'll buy the machine if you can make a shaft. We can make a hole which is 10 micron in diameter. And we had to do it. Initially, I thought I would say impossible, but I scolded IIT Delhi guy to say impossible. How can I say to Panasonic guy, they may have some solution. So I kept on thinking about it. I told my engineers and PhD students to do it. They all said impossible, sir. But I said no, take the challenge, do it. And then we started our journey. Then first of all, we sat down to find out. First of all, again, I tell everybody to think about the problems, why you cannot do it. When we thought about 10 micron hole, because we thought, okay, 10 micron hole, our shaft should be about 7 or 8 micron in diameter. How to machine that shaft? That was really a difficult problem for us to solve. All of us sat down and discussed. And we analyzed what is the problem. When you have a tool from the market, which is usually, for micro machine, the edge radius is 100 micron. So what will happen when you go smaller and smaller dimension, the radial force will be significant. So it will bend the shaft. Okay? So then we agreed that we should remove the edge radius, make this edge straight. And as I told you, we try to use infinitely strong tool. We use diamond tool to machine any material, but not single crystal diamond. We use polycrystalline diamond, okay? Because a single crystal is very expensive. So we use polycrystalline diamond. The student and researchers all said, sir, how to remove the cutting? This edge, it's a diamond tool. And I said, do EDM to remove it. So they ridiculed me, sir, how to EDM diamond? Cannot be done. I said, hey, luckily, the tool is polycrystalline diamond. You can do EDM on it. Because when you do EDM, the bonding, which is cobalt, the bonding falls off. So the diamond particles fall off. And that way, you can do it. Oh, equation. Yeah, so all these equations are there. Anyway, so what happened? We did EDM on it. It's called block EDM. And we, using block EDM, I'll cover it later. We remove the edge radius and become straight. The shadow is there actually. So this is straight edge. You'll have to have some clearance. And with that, we machined. And the steps are, first of all, you do conventional machining, and then you get a diameter like this, and the tool, then you sharpen it by removing a cutting edge, and finally you get a tool with no edge radius, and you can get a shaft up to, what we achieved is up to 5 micron. So you'll have to bring in, how many compounding you look at it. First of all, you take a diamond tool to the machine, and then remove the edge radius by EDM, and bring in that tool to do machining, and that also we could achieve up to 11 micron. So our hole should be 10 micron. Then what we did on that shaft, we did again EDM, and that time it was wire EDM to reduce it to 5 micron. And then we made a hole which was 6.5 micron. So many processes you had to compound together, and only such a machine can do it with a zero setup error. Because one setup, you continue to do many processes. Right? So compound machining is necessary. Machine for compound machining is necessary. Okay? Finally, we got the shaft through processes. And finally, we got 11 micron. That was not enough. On that, we had to do block EDM on that 11 micron shaft. And continuously, we were measuring it. And finally, we get a shaft which is 5 micron. And with that, we got the hole. And this is the hole. The student, in the paper, first author was Asa. Second author was Arthur, who was my student. And he did it. 2 a.m. at midnight, he called me, and I was very upset. But then he called me, sir, I have done it. So I was very happy. I went to the lab and saw that he has successfully done it, and he done this 10.5. Then I said, hey, it could be fluke. But he said, no, sir. I was there. He machined 6.5 micron, 8.5, 10.5, 12.5. So it is doable. So coming back, you will have to know compound machining, and you will have to think what are the processes to apply, how to apply, and very judiciously, very efficiently you will have to apply. So all these things you will have to remember when you do go for any project, any research. Because this is the whole 6.5 micron, highly accurate. So rest of the thing, all examples will be on compound machining. This is milling, and this again by milling we can machine this type of 37 pins, and in milling you can do two ways. Milling, if the pin is square, then it's very simple. You do straight milling. If the pins are round, then you will have to rotate the cutter. After getting the square pins, you will have to rotate the cutter around one pin. Okay? Then space should be enough, or the cutter should be very small in diameter. Those steps you will take later, no doubt. And one of the round pins, with that we can machine this. And this can be, after machining these pins, you do reverse EDM. You can do reverse EDM, or you can do direct EDM. You can get all these holes. Rest of the things, this one I've already covered. And then again, when you try to do EDM on very small rod, usually you can do block EDM, you can do disc EDM, you can do wire EDM. Do I need to elaborate on it? Or block EDM is very easy. When you use a block, rotate the electrode, and the block gets worn out, and electrode also gets worn out, and finally you get the shape. It is, accuracy is not very high. You can use a disc to do it. This is okay. But when you do wire EDM, it takes very long time, but accuracy is very high. This example, I skip those. These are more examples. And micro holes, I think I skip all these things. These are all jobs done. Small pyramid machined using EDM. And wire EDM, this one you see, this solid block around in the center between two channels is highly accurate. It is 2 or 3 micron machining time. Width of the thickness of this is 2.5 micron. Extremely accurate one. So these are the things. And these are skip. On an injection needle, we cut slots. These are skip. We have the vibration device. Vibration, why we need vibration? When you do EDM, the debris disturbs the EDM. If you vibrate the workpiece, the debris cannot stick to the, neither to the workpiece nor to the electrode, then you get accurate hole faster. Recently we have developed, this is very low frequency vibration because we just want to disturb the debris so that they cannot stick to it, or they cannot create the secondary electrodes. What we have done actually, we have developed recently ultrasonic vibration device. This is an order we got from Turkey to make. We said, hey, useless, why do you do it? But while we developed it, we found ultrasonic vibration device is much useful and efficiency is much higher. These are the holes machined, wire cut EDM. So these devices I will skip. This was interesting. To develop very widely used nowadays, developing micro channels on glass. Initially, we never thought about it. Then our fluid mechanics division, they wanted to do a research on simulate the blood flow on glass because non-reactive to blood. So, but initially we thought how to do it. Our machine is not, it's not machining, simple machining. So we had to do it for them. And what we did, very quickly I'll go through, we bought these PCD rods. On PCD rod, we did iridium. So what happened, PCD rods bonded by cobalt, as I mentioned, the cobalt dropped and diamond particles came out, protruded, became the tool, and with that we did milling. You can call it grinding or you can milling. So using the PCD tool, removing the diameter, getting the desired diameter, and do milling, diamond milling. That way you can fabricate the tool and you can cut glass. This was one of the PhD project. So you need to do compound machining in all the cases. And the machine is, surface is so smooth, nano finishing. And from there I got the idea how to do ductile mode machining of brittle material. Then I went into actual machining of silicon using diamond tool, ball and tool we used, and I'll explain when I talk about milling, ductile mode machining of brittle material using milling. I'll quickly finish it, and then we went for laser because I told you we needed to use laser. Oh, this is for measuring. Measuring device, you don't have to know details. Laser machining, I'll cover it somewhere, it is there, one of the slides. We compounded laser with the machine, then we did laser machining first, and then we did iridium, and it is very fast. This measuring device I will. Now, diamond turning, 1 o'clock, I think it is very long. Shall we stop here? And this again, I will give the examples of compound machining. Just diamond turning alone, usually silicon machining, silicon slicing and machining, all were done by grinding. And grinding is, as I told you, is not a good process. It gives micro cracks. You see the mirror finish, actually there are cracks. Whenever you go for grinding, you will have subsurface damage with cracks. So it is not the solution. You will have to go for machining, and you will have to do ductile mode machining of brittle material by turning or milling, whatever it is. That time we had a machine from Japan, from Toshiba, and we started with that, and material was silicon or nickel plated material, a single crystal tool. But the thing is, I think I skipped that. I will cover more in detail when we go for ductile mode machining. Oh, this one is interesting. Ductile mode machining I will introduce later. But the thing is, when you do machining in diamond turning, fine, you can get a surface. But if you want to generate feature on the surface, with a single tool moving in one direction or even in two directions, if it doesn't have another secondary motion, then you cannot have features. Right? I hope you agree, you are convinced. So to generate feature, that was my project, to have a secondary motion on the tool. So tool we had to vibrate at ultrasonic vibration. So using first tool servo, which is a piezo actuator, which can very small amount of vibration depending on the amplitude of vibration of the piezo actuator. So while the tool is moving along this path, it can move in Z direction as well. So while it is cutting in Y direction, sorry, if you take it X or Y, X direction, if you take it Z direction, you can machine along this and you can generate feature on the surface. And all these details I'll skip. Piezo actuator is there on the tool, and you can control the form accuracy, control the surface finish. If you do not use this first tools of a piezo actuator, your surface finish is of this order. Okay, about 4 micron, Whereas if you use piezo actuator, a machine brass or aluminum, this is the roughness, but when you use first tool servo, your surface finish is almost zero. So we had to bring in first tool servo to get correct dimension, correct accuracy. All these examples. And then generating features. There's the form, error, accuracy. You can generate all these features. Lens arrays, pyramid arrays. So this is one. And then these are to generate feature. But when you come to machining soft material, it is all right, diamond tool you can use. But when you try to machine tungsten, even diamond tool is a failure, correct? So if diamond tool cannot do machining tungsten, then what to do? Is there any other way? What is the enemy? Enemy is the cutting force. Now if you try to reduce the cutting force by machining, what is the way to do it? Yeah, vibration. But if it is one directional vibration, every time it is hitting the same point of the tool, correct? And chip thickness is constant. So if you can reduce the chip thickness, please think about it, reduce the chip thickness, your cutting force will go down, cutting will fall. But how to reduce the chip thickness? You have the limit. But with same depth of cut, how can you reduce the chip thickness? Then to reduce the cutting force, then with the professor in Nagoya, Shamoto, we started a research on not direct cutting every time hitting. Can you think of something? Have you ever heard about it? The tool with not direct ultrasonic vibration straight, elliptical vibration. If you apply elliptical vibration, look at the tool travel path. This is a vibration device, and we apply elliptical path and giving two modes of vibration, longitudinal and transverse, second degree and fifth degree, if I'm not wrong, fifth. Yeah, combination of second degree resonant mode of longitudinal vibration and fifth resonant mode in bending vibration. So compounding together, we got a tool path which is like this. The tool comes in contact, it digs in and moves out. So it takes the chip, the radial force working on it, and it moves out. The secondary friction on the rake face is negative. It pulls the chip. So the rake face is very safe, it doesn't wear off, the tool wear drastically falls, and chip thickness becomes much thinner. Force becomes less, frictions become less, tool life becomes infinitely large, surface finish is extremely smooth. So that way, if you introduce elliptical vibration device, you see, so you'll have to come out with newer and newer processes, newer and newer methods, then you can machine even harder and harder material. All these details I'll skip. You can vary the dimension of this elliptical path A and B. You play with parameter to get the optimum dimension. Okay? And this is the device. Finally, this has been given to a company. They develop and commercialize the product. If you look at a tungsten piece using PCD tool, and if all these measurements are there, finally, I think when I talk about diamond turning, I'll talk about it. And using even a PCD tool, you can machine tungsten very safely. A single crystal diamond will give you about 2 nano surface finish. PCD tool give you about 4 nano surface finish. If you try to do it ultrasonic vibration, single degree, single direction, and you cannot even machine it. So all these things I try to quickly cover. Every stage you need compound machining. Most of the things you can solve if you can follow compound machining process. So with that brief introduction of different machining processes, I'll go into the details of each and every process from next lecture. Okay, any question? I know that those who are not in that area, diamond turning, they will not like it. Those who are in EDM, they may not like the other. But try to follow, because this will be useful. This is the only platform where you don't have to listen it from different lecturers. I can try to introduce all the processes to you. If you have any question, please. Yes.
Thanks, sir. Thanks for a nice presentation. So I have one question. So how to check the setup error?
How to
check?
How to check the setup error?
Yeah.
No. Setup error you can do in optical way. There are various optical devices. If you can install optical measuring device. Are you talking about initial setup error?
Yes.
Yeah. That way, simply you'll have to use the optical devices. Camera. Very high magnification camera. Then you calibrate the system where your initial tool is touching on this side and the other side, you can get the exact dimension. After machining, you again bring the camera there. You can set how much you have machined. Is it the exact dimension or not? If you use touch probe, it is almost impossible. You'll have to have high resolution optical measuring device. Yeah. And once you set it, it is done. Whatever and how many machining processes you apply, you will get the correct dimension. And resolution should be very high so that you can get high accuracy. Any other question?
I am Srinivas from Bangalore. In all beam processes, deflection will be the major problem. You mentioned about laser beam micro machining. Will not the laser beam deflect? And how it linked with the thickness of the material?
Okay, laser beam. When you come to machining, I may be wrong. If I'm wrong, excuse me. I can study it more in detail. But when you laser beam machining, when you talk about measurement, long distance measurement, milli or so on, in laser beam machining, the gap between the object and the focal point, machining point, is very limited. Because you'll have to calculate correctly what would be the energy released by the laser beam, how far the distance should be. Distance is so short that you'll have minimum error. And one more thing, in laser beam machining, I say laser beam machining is not, it is only a rough machining process.
Okay.
We never use laser beam machining for fine finishing. We use the first primary process and then finish it by other process like EDM.
Okay. And second one is on micro drilling.
Yes.
How to get the tool signature like flute angle, helix angle, etc. on the drill bit in
That
micro drills?
Okay. Let's just take, okay, again my answer may not be exactly correct. Usually micro drilling we do not expect nano accuracy of the hole. We are very much, we put our attention to get that few, for instance, 50 microns, 30 micron holes.
No, how to get the tool angles in the drill bit, micro drill bit? Tool signature.
Okay, that all supplied by the manufacturers. We do not assign anything to them. As they supply it, we use it to get the diameter.
Okay, so tools are not manufactured directly, you get from the manufacturer.
Yeah, tool we get from, if it is a tool, if it is conventional tool, we get it from the manufacturer. If it is by other processes, EDM, we don't have to bother about angles and so on.
Okay.
So usually we do by EDM, and if it is by conventional tool, we leave it to the tool manufacturer. Okay. Now I'll touch later when we can have first drilling by EDM. That will be one topic, combining arcing and sparking together. Hopefully we can get rid of that problem. Conventional drilling can be replaced by compound machining. Yeah.
Hello, myself is Hardik, and my one question is that you mentioned fabrication of micro grinding tool using BEDG process. So can you brief about BEDG process?
I didn't get your question.
Yeah, in one of the slide, there is you mentioned that fabrication of micro grinding tool using BEDG process.
Oh, block, shortened form, block.
Electron discharge grinding.
I showed you the example. When you get, for instance, when you try to get your desired dimension, for instance, you get an electrode for a PCD rod. It comes usually, if you want 80 micron diameter, you buy a 2 millimeter diameter. Because if you buy 1 millimeter, then you clamp it. After machining, you cannot. 1 millimeter should be all right. If you get 1 millimeter rod, then you clamp it. Then to make it fast, you use block EDM. I showed the example with the block, and then to get the finer dimension, you can wire EDG. But that abbreviation came from all these processes used.
Yeah, but then when we do the BEDG on PCD tool, then all diamonds also are eroded, so we cannot get the sharp edges exactly to the grinding beams.
What were the reasons that you cannot get exact dimension?
I am trying to say that we have micro grinding tool, and we applied that block electrode grinding, and we have done some centering and everything. But when we apply BEDG process, that diamonds, sharp edges of the diamond, that is also eroded. So how we will do the machining after that process?
No, that is the thing. Your block is wiring. I hope I have got your question. Your block is also wiring off. Your electric is also wiring off. This happens in all EDM processes. Even if you do conventional EDM, electrode wires off, workpiece wires off, correct?
Yes.
So that factor you will have to know. Again comes the complication, which one is your anode, which one is cathode, forget about it. If we say that your electrode is anode, which will wear off, but yet still the block will wear off, correct? That will have to see how much wears off. It will have to be a little bit of trial and error.
So we have the PCD block. I mean, we assume that we have this diamond grids,
Yes.
or the PCD grids basically, and they are bounded together with the cobalt.
Cobalt, yes.
Now, I think what he means, we start EDM action.
Yeah.
So basically, we are assuming that this cobalt is getting affected and the grids are falling
It's
off.
coming out, yeah.
So his question is there any erosion action happening on the diamond?
No, diamond remains ineffective.
Yeah, because if that erosion is happening on the diamond, then it will smoothen it out rather than leaving a shaft.
No.
Yeah.
Diamond, there is no effect on EDM on diamond. Yeah, only the cobalt falls off. Cobalt melts and it falls off.
Yes.
Yeah, particles are not affected. Particles are not affected because we are not doing any grinding of the diamond particles. Diamond particles remain intact. Only the cobalt melts and falls off.
Yeah.
Yeah. Sorry. Yeah. Otherwise, it will be purpose will not be solved. Thank you. Sorry, I couldn't get it.
Related query.
Yeah.
Because we are basically doing the EDM action over there.
Yeah.
It's a heat-based process. Of course, it is not eroding the diamond grids.
Yeah.
But at the same time, the heat is happening. So that heat, is that sufficient to change the properties of the diamond? Basically, the amorphization. And that leads to the degradation of the diamond.
Yeah.
So is that issue?
Yeah, that could be, but we did not see any effect. In that case, if it would happen, then we would not be able to do the machining of glass. Yeah. If you ask the second question, I will put in the question into your mouth, then I will say that I will study and come back. But we did not see any effect of erosion of the diamond or any distortion or machining of diamond itself, no. Why? Then I'll have to come back and answer your question. Any other question?
Sir, there were three terms mentioned: simultaneous machining, simultaneous, then compound, then hybrid. Now, how do we distinguish between them?
Okay, compound and hybrid. Okay, hybrid is, if I'm wrong, you tell me. What I mean is two processes run simultaneously. Hybrid process. Compound is one follows the other. Okay? agree, that is the way I differentiate. Hybrid is two processes together.
Sir, I am not laser micro machining related, but during research work, I just come to know that while machining of non-conducting materials, laser machining, micro machining is not suitable process for machining of non-conducting materials.
No. Micro machine is effective for both. Okay, let me try to explain. If it is EDM, then you cannot carry out EDM if the material is non-conducting.
Yes, I know
Yeah.
that. Yes,
sir.
You are right, sir.
So you can micro machining you can do on conductive and non-conductive both. Yes.
But as far as literature shows that the micro machining of different non-conducting materials like quartz, zirconia, it is not suitable for laser machining. Why?
Okay, zirconia and so on.
At a micro level.
Laser machine
Means micro slots, micro grooves. It cannot be easily produced by the laser micro machining. As far as the metal is concerned, it is good for laser cutting.
Yes.
What is the main disadvantage of it?
Laser cannot be used for non-conductive material.
Sir, actually my research process is not relevant to laser machining, but during literature survey I found that non-conducting materials cannot be easily machined by the laser, and the metals can be easily machined by the laser machining at a micro level.
Is it true? I don't know. No. Laser is, after all, you are generating a heat source. Yeah. Please go ahead.
Okay, I mean, just couple of points. When you do the laser machining, it's not whether it's a conductive or non-conductive.
Yeah.
That is not a main issue.
Yes, sir.
Basic issue is about the optical properties. Okay, so whether it is conduction of, when we deal with the lasers, we are talking about the optical source of energy. If your material is able to absorb that optical energy, then that is a good candidate. It has nothing to do with the thermal conductivity or the electrical conductivity.
So it depends on optical properties of.
Yeah, so that's the reason. I mean, if your material is good optical absorption, now optical absorption will depend on the wavelength. Okay, so first thing we should consider, what material you're using and what optical wavelength. Not that you bring any laser, it will machine the same material. Okay, so this is one thing. And second, the conductivity, as you mentioned, thermal conductivity plays a role. That's where the metal and the ceramics, they are going to be different.
Yes.
Because once you apply a laser heat source, if everything is getting conducted away, then you are not going to get the laser heat concentration. It will not machine it. Particularly, it will be a problem in case of your micro machining. Yes. Because it's getting concentrated and too much heat damage done, and everything is, there is no control. And if it's too much conductive, everything is getting conducted away. It's just heating up. It's not melting it. So there are a lot of other parameters. It's not just what you said is the conductive, then it is, you cannot make that statement in that sense.
Thank you, sir.
Okay, good. Thank you very much. Those part, definitely laser generates the heat. So whether the heat is effective on that material or not. Thank you very much.